Hello students, welcome to my channel Engineers Academy. Let's solve this particular problem. In this problem it is said that write shear and bending moment equations for the beam loaded is shown and sketch the shear force and bending moment diagram. So we are given this loaded beam and we are required to find the shear force and bending moment equation, and we are required to draw the shear force and bending moment diagram for this loaded beam, right? So first of all, at this point E and C, we have some supports, right? So only the reactions of their supports are given. So that reactions are represented by this R1 and R2. So to solve this problem, first we need to find this R1 and R2. So as I have discussed, to find this R1 and R2, we have to represent that distributed load by its corresponding concentrated load. Right. So here at point A we have that R1, right? This is that R1, and here we have this distributed load which is acting along the 5 meter length from this point A. So if we want to represent this distributed load by its corresponding concentrated load, so then that concentrated load magnitude will be equal to the area of this distributed load, right? So if I represent that distributed load, that concentrated load which will replace that distributed load, so that concentrated load will be equal to 5 times this 20. So this will be equal to 100 kilonewton, right? So this 100 kilonewton force replaces their distributed load, right? And as we know that this 100 kilonewton force the line of action of this 100 kilonewton force will pass through the centroid of this rectangular area, and as we know that the centroid of this rectangular area will be located at half of the length of this 5 meters, right? So from this we say that this 100 kilonewton force will be at a distance of 5 divided by 2, and 5 divided by 2 is 2.5 meters, right? So this 100 kilonewton concentrated load which replaces this distributed load will act at a distance of 2.5 meters from this end point A. Similarly, at point C we have this R2. So let me draw that. Here we have that R2 like this, and R2 is unknown, and this is that point C. And at point D we have that 30 kilonewton force which is acting vertically downwards. So this is that 30 kilonewton force at point D. So now to find these reactions, if I apply the summation of moment about point C equals to 0, so as we can see that this R1 is producing the clockwise moment, so I will write minus R1, and the perpendicular distance of this R1 from that R2 is 10 meters, which is given here, right? So I will multiply this with 10. Similarly, this 100 kilonewton force is producing the counterclockwise moment about that point C, so I will write plus 100, and the perpendicular distance of this 100 kilonewton force from that point C is this distance, and this distance is 10 minus 2.5, right? So we can say that this is 7.5 meters. Similarly, this 30 kilonewton force is producing the clockwise moment about this point C, so I will write minus, this is 30, and the perpendicular distance of this 30 kilonewton force from this point C is 4 meters, right? It is given here, this is 4. So I will multiply this with 4, and this is equal to 0. So from this we can find this R1. So R1 will be equal to minus 100 into 7.5 plus 30 into 4 divided by minus 10. So R1 is equal to 63 kilonewton. So R1 equals to 63 kilonewton. So here we can write that this R1 is 63 kilonewtons, right? And similarly, if we apply the summation of forces along y equals to 0, if this is our positive x and y direction, so as we can see that this R2 is acting in the positive y direction, so I will write R2. This R1 is acting in the positive y direction, so I will write plus R1, and R1 magnitude is 63. This is acting in the negative y direction, so I will write minus 100, and this 30 kilonewton is acting in the negative y direction, so I will write minus 30, and this is equal to 0. So from this equation we can find R2. So R2 will be equal to minus 63 plus 100 plus 30. So this is equal to 67 kilonewton. So I will write that this is 67 kilonewton. So here R2 is equal to 67 kilonewton. So now we know R1 and R2. After this, to find the shear force and bending moment equations, since the shear force and bending moments are the internal force and moment, so what we will do is that we will pass imaginary cutting section, right? So we will pass a cutting section at this point, right, between A and B. Then between A and C we will pass another cutting section, that is the BB section, and then we will pass a cutting section CC between C and D, right? So first of all, what I will do is that I will pass a cutting section between this point A and B, and we will consider that free body diagram, right? So after passing this cutting section, we will have the free body diagram until this section, and the length of this section will be equal to x, since we are measuring the x from this point A, right? So this means that so this will be our section. Here we will have that R1 is 63 kilonewton, and here from this point to this point we have that distributed load, right, and this is 20 kilonewton per meter, and the length of this section of that beam is x, right? And here at the right side of this cutting section we will have the bending moment, internal bending, like this. So let's say that this is that bending moment, and here we have that shear force. Let's say that shear force is represented by V, right? So to find this shear force and bending moment equation, what we will do is that we will replace again this distributed load by its corresponding concentrated load, right? So this is 20 kilonewton per meter. So to replace this distributed load by its corresponding concentrated load, so that concentrated load will be equal to the area of this distributed load, which is 20 times x, right? So I will write that this is 20 x kilonewton, right? So now if I apply the summation of moment for this section, right, which is between point A and B, so if we apply the summation of moment, or if we apply the summation of forces along y equals to 0, so this is the positive convention for the shear force and bending moment. So we will consider these as the positive directions, right? So this means that shear force is acting vertically downward, so this is the positive direction, so I will write plus V. This R1 is acting in the negative direction, so I will write minus R1, and R1 magnitude is 63, and this is acting in the positive direction, so I will write plus 20x, and this is equal to 0, or from this we can say that V is equal to 63 minus 20x, right? So this is the shear force equation when x is greater than 0 and less than 5 meters, right? Since we have considered the cutting section between point A and B, and the distance between point A and B is 5 meters, right? So now if we draw the shear force diagram, so along the y-axis we are representing that shear force equation, which is in kilonewtons, and along the x-axis we are considering the length in meters, the length of the beam in meters, right? So now from this equation we can say that when x is equal to 0, the shear force is 63 kilonewtons, right? This equation is in kilonewtons, remember, right? So now we can say that if this one box is 50, so this is 100, so let's say this one box is 30 and this is 60, so 63 will be somewhere here, right? So we can say that, let's say that somewhere here is that 63 kilonewton shear force, right? So, and if we equate this equation equals to 0, if we say that if v is equal to 0, right, so then we can say that this equation 63 minus 20x, this is equal to 0, or we can say that 63 is equal to 20x, or from this equation we can say that x is equal to 63 divided by 20. So 63 divided by 20, so this is 3.15 meters. So from this we can conclude that at x is equal to 3.15 meters, the shear force is equal to 0, right? So let's say that this one box represents 1 meter, so 1, 2, 3, so 3.15 will be somewhere here, right? And as we can see that this shear force equation is a straight line equation, right? So we can join this 63 kilonewton force until this point, right? And similarly, if we put x is equal to 5 in this equation, that is 63 minus 20 into 5. So this is minus 37. So at x is equal to 5, the shear force is minus 37 kilonewton. So this is 1, 2, 3, 4, 5. So somewhere here is that 5 meters, right? So at 5 meters, we have 37, right? Somewhere here is that 37. So this means that this line will pass through the x-axis at 3.15 meters, and it will continue, since it's a straight line from x is equal to 0 until x is equal to 5 meters, right? So let me draw a continuous line from this 63 kilonewtons until that point. And remember that this point is at 3.15 meters, right? So from x is equal to 0 until x equals to 5 meters, this is the shear force distribution along the length of this loaded beam. Similarly, if we apply the summation of moment at this point A, here we have that point A. So if we apply the summation of moment about point A equals to 0, and if we assume that this is the positive direction, so this is plus m, right? And as we can see that this 20x force is producing the negative moment, right, according to this convention. So we will write that this is minus, this is 20x, and the perpendicular distance of this 20x from this point A will be how much? So it will be half of the length of this beam, right? Since the centroid of this rectangular area will be located at a distance of x divided by 2 from this point A. So we can say that this will be x divided by 2, since the length of this section of this loaded beam is x divided by 2. So I will multiply this with x divided by 2. And similarly, as we can see that this V, this shear force is producing the negative moment about that point A as well. So I will write minus V, and we know the V equation. So V is 63 minus 20x, and the perpendicular distance of this V from that point A is x. So I will multiply this with x, and this is equal to 0. So we can simplify it. So we can write that this is m. This will be, so we can write that this is minus 10x square minus 63x. This is minus into minus plus 20x square, and this is equal to 0. And similarly, we can write that this will become 10x square. So on the other side, it will become minus 10x square. This will become positive. So this will become 63x minus 10x square, and the units of this will be in kilonewton meter. So since it's a second degree equation, so we can plot it as well, right? So let's say that this is again along the y-axis, this is our moment, which is in kilonewton meter, and along the x-axis is x, the length in meters, right? So now if I put x is equal to 0 in this equation, so the moment is equal to 0. So this means that at x is equal to 0, the moment is 0, right? And similarly, if I put that 3.15 at which the shear force is 0, so this will be 63 into 3.15 minus 10 into 3.15 square. So the moment is 99.23. So I will write that the moment at x equals to 3.15 meters is equal to 99.23 kilonewton meter, right? So let's say that this box represents 50 kilonewton meters, so this will be 100. So at x is equal to 3.15, somewhere here we will have that 99 point something value. So let's say that 99 point something is here, right? So as we can see that it's a second degree equation, so it will be a curve like this, right? So let me find somewhere the moment value at x equals to 1 meter. So if I put x equals to 1 in this equation, 1, so this gives us 53. So at x is equal to 1 meters, the moment value is 53 kilonewton meters. So we will be having that somewhere here, right? So I will draw a freehand moment curve, right? And at x is equal to 5, if I put x equals to 5 in this equation, this is that moment equation from x equals to 0 until x equals to 5 meters. So we will have 65 kilonewton meter, right? So at x is equal to 5 meters, the moment is equal to 65 kilonewton meter. So this is x is equal to 5, this is 50, so 65 will be somewhere here, right? So then we can join it like this. So this is the bending moment curve until x equals to 0 until x equals to 5 meters, right? And I will write the equations, the corresponding equation. So this line is represented by 63 minus 20x, and this curve is represented by 63x minus 10x square, and here we have 99.23 kilonewton meter moment, right? Now to find the shear force and bending moment equation from this point B to C, we will consider another imaginary cutting section between this point B and C, and then we will consider this section from A until this point, right? So let me write here. So this is that point A, and somewhere here we will have that point B, right? And then we have that cutting section. So until from A until point B, we have that distributed load. So now we can replace this distributed load by its corresponding concentrated load. So that will be acting somewhere here, and the magnitude of this concentrated load will be the area of this distributed load, which is 20 times 5, which is 100 kilonewton. And we know that this 100 kilonewton is at a distance of 5 divided by 2 from this point A, which is 2.5 meters. Here we have that R1, which is 63 kilonewtons, right? And again we will have shear force here, and we will have the bending moment here, and these are the positive conventions, right? So now this will give us the the shear force and bending moment equation from x greater than 5 meters and less than 10 meters. So now if I apply the summation of forces along y equals to 0, so this is the positive v, so I will write plus v. This is acting in the negative direction, minus 63, and this is plus 100, and this is equal to 0. V will be minus 37 kilonewton, right? So this means that from x greater than 5 meters until x equals to 10 meter, the shear force will remain constant, that is minus 37 kilonewton, right? So here we have that shear force value which is minus 37 kilonewton, right? So until x equals to 10 meters, it will remain constant, right? So this is 6, 7, 8, 9 and 10. So until here, this shear force diagram will be a horizontal line like this, right? And similarly, if we apply the summation of moment about point A equals to 0 for this diagram, so again as we can see that this is the positive moment, right? So we will write plus. This 100 kilonewton force is producing the clockwise moment that is in the negative direction, so I will write minus and 100, and the perpendicular distance of this 100 kilonewton force from that point A is 2.5 meters, so I will multiply this with 2.5, and this V is producing the negative moment, so I will write minus V, and V magnitude is minus 37, and the perpendicular distance of this V from that point A is the length of this section, and the length of this section is again x, right? Since it's an imaginary section from this loaded beam from this point A until somewhere here, right? So the length of this cutting section is also x. So we will multiply this with x, and this is equal to 0. So from this we can write that minus 250 plus 37x, and this is equal to 0, or we can say that the moment is 250 minus 37x, and this equation, the unit of this moment is also in kilonewton meters, right? So now again if I put x equals to 5 meters in this equation, so we will get that same value that we obtained here, right? So let me put, this is 250 minus 37 into 5. This is that same 65 value, right? Here we have the moment equals to 65 kilonewton meter, right? And as we can see that again this is a straight line equation. So if I say that if I want to find the x value for which the moment will be equal to 0, so I need to equate this equation equals to 0. So if we write it as 250 minus 37x equals to 0, so we can say that x will be equal to 250 divided by 37. So 250 divided by 37, so this gives us 6.756, or we can say that it is 6.76 meters. So at x is equal to 6.76 meters, the bending moment will be equal to 0. So this is 5 and this is 6, somewhere here is 7, so 6.76 will be somewhere here, right? So here the bending moment will be equal to 0, and at x is equal to 10 meters, if I put x is equal to 10 in this equation, this is 250 minus 37 into 10, so that gives us minus 120. So the moment at x is equal to 10 is minus 120 kilonewton meter, right? And here this equation represents the straight line equation, right? So now at x is equal to 10 is 5, 6, 7, 8, 9 and 10. So this is 50, 100, so 120 will be somewhere here. So we will join this particular point with this point, right? And it will pass through the x-axis at x equals to 6.76, right? So I will write here that at this particular point, this is x equals to 6.76 meters, right? Now we will find the shear force and bending moment equation from x equals to 0 until x equals to 14 meters. Sorry, from x equals to 10 until x equals to 14 meters, right? Here we have that x equals to 10 meter, and here we have that x equals to 10 meters, right. So now we will consider the imaginary cutting section between this point C and D, right, and then we can consider the free body diagram either on the right hand side of this cutting section or on the left hand side of this cutting section, or we can consider it on the right hand side of the equation. So as we can see that on the right hand side of this imaginary cutting section we have less number of forces, right. So normally it is recommended that you people need to consider that side of the cutting section where we have lesser number of forces. So I will consider this cutting section, but since we are measuring the x from this particular point A, so this imaginary cutting section is at a distance of x from that point A. So then the length of this section will be equal to 14 minus x, since the total length of this beam is 5 plus 5 plus 4, which is 14. So and this imaginary cutting section is passing at a distance of x from that point A. So the length of this section will be 14 minus x, right. So we can write that this is 14 minus x, right. So now if I draw the free body diagram, so we will have it like this. So here we have that point D now, right. This is that point D. So at point D we have this 30 kilonewton force. So I will represent that 30 kilonewton force here. And now we are considering the left hand side forces and bending moment. So let's say that this is that bending moment and this is the shear force. These are the conventions, right, for the left hand side of the cutting section. So this is V. So now if we apply the summation of forces along y equals to 0, so this is the positive convention. So we will write plus V minus 30, and this is equal to 0. So we can say that this V is equal to 30 kilonewton. So this means that from x greater than 10 meters and less than 14 meters are equal to 14 meters, we can say that x equals to 10 meters until x equals to 14 meters, this V will remain constant and it will be having plus 30 kilonewton value. So now we can say that here the diagram will shift to plus 30, right. So since this is 30, so we will draw the diagram like this, and it will continue until 14, right. So this is 10, 11, 12, 13, 14. So we will have somewhere here we will have that horizontal line like this, right, and this is plus 30 kilonewton. Similarly, if we apply the summation of moment about point D equals to 0, so as we can see that this is the positive convention, so I will write plus m, and V is producing the positive moment as well, so I will write plus, and V magnitude is 30 and the perpendicular distance of this V from that point D is 14 minus x. So this is equal to 0. We can say that this is plus 30 into 14, this is 420 minus 30x, and this is equal to 0, or we can say that this is minus 420 plus 30x. So again this is a straight line equation, right, and if we put x equals to 10 in this equation, this is minus 420 plus 30 into 10, so this will give us that minus 120. So again at x is equal to 10 meters we have that minus 120 kilonewton meter value. And similarly at x is equal to 14, if I put x is equal to 14 in this equation, so that moment is equal to 0. So m at x is equal to 14 meters is equal to 0. So here we have that x equals to 14. So since it represents the straight line equation, so now we can join this particular point to this particular point, right? So this is the corresponding shear force diagram, and this is the bending moment diagram for this loaded beam. And from x equals to 0 until x equals to 5 meter, this is the equation for the shear force, and from x equal to 0 until x equals to 5, this is the bending moment equation. This is 63 minus 10x square. The maximum moment occurs at x is equal to 3.15. If someone asked in the question, if we were asked in the question that find the location along the x at which the moment will be maximum, so we can say that at x is equal to 3.15 meters, the bending moment is maximum, which is 99.23 kilonewton meter, right? And similarly, from x equals to 5 until x equals to 10 meter, the shear force remains constant, and that value is minus 37 kilonewton. And similarly, from x equals to 10 until x equals to 14 meters, the shear force again remains constant, and that the value is 30 kilonewton. And similarly, from x equals to 5 until x equals to 10 meters, the bending moment equation is a straight line equation which with a negative slope, right? It is having negative slope. And from x equals to 10 until x equals to 14 meters, the bending moment equation is this minus 420 plus 30x, right? And it is with the positive slope, and the slope is 30, right? So this is the solution of this particular problem. I hope this will help you in learning how to draw the shear force and bending moment diagram. If you people think that all my videos are helping you in building the concepts related to engineering statics, so kindly subscribe my channel and like my videos so that I can solve such more problems.